Okay, thank you, Mark, and good morning to everybody. Let me dispel a myth. I did not work on Viagra, so for you. Over the past several years, my topic today with Will Happer is essentially climate change. This is a controversial subject. We all have vested interest and views on this. My own opinion on this is I want to open this topic up to scientific inquiry and dialogue, as opposed to the monolithic opinions that we see from time to time on the subject and the alarmist nature of warnings regarding this. Professor Happer has just recently returned from a speaking tour in Australia on this very topic. He has a long and distinguished career in academia, government, and private industry. He's now professor emeritus of physics at Princeton University, and essentially many of his subspecialties have a great bearing on this topic. He also was scientific advisor to the Bush and Trump administrations. He is a PhD from Princeton, a BS in physics from the University of North Carolina. He formerly taught at Columbia University, co-founder of several organizations designed to bring scientific inquiry back to this controversial subject. He has published over 200 peer-reviewed articles. He's a fellow of the American Physical Society, a member of the American Academy of Sciences, the National Academy of Sciences. He's received numerous awards, which I can't enumerate at this stage. He's married, lives in Princeton, and has 2 children and 6 grandchildren. And without further introduction, I present Professor Will Happer to talk about this topic. Thank you.
Well, I do thank Mike Martin and his colleagues for inviting me here. I'm honored to be here with so many distinguished people. And I'm going to talk a little bit about carbon dioxide, which is the gas of life. And let me see if I can get this to operate here. Just a minute. Yeah, I want to get full screen. Okay. That won't go full screen. Yeah. Okay. Good. And here, cut this off. Yep. And then how do I advance it? Right click. No, that doesn't work. Oh. Okay. Good. All right. Good. All right. So let's see. That's good. You know, when I came this morning, I brought a CO2 meter, and you probably know that if you go up a few thousand feet, the CO2 concentrations in our atmosphere today are around 430 parts per million. We have observatories all over the globe that measure this very precisely. You have to go pretty high before you get a stable reading here near the ground. It varies all over the place. I went out into the cemetery half an hour ago, and I brought a meter here to measure the CO2 concentrations. And I just mentioned that above our heads, it is 420 parts per million. And I'm going to measure it in this room here, but when I measured out in the cemetery, it was 530. So why do you suppose it was 530 in the cemetery, but it's much less higher? Does anybody know? Okay, well, the answer is, you know, if you have one of these, it's kind of interesting to go in your backyard and do a 24-hour record. What you'll find is that in the morning like this, CO2 levels are very high because all night, you know, the living creatures in the soil, the plants have been respiring CO2 into the air. So the air near the ground is full of CO2. If you go out in the late afternoon and you do the same measurements, you typically find maybe something in the 300s. So just from day to night, CO2 levels where we live go up and down by 100 parts per million. And that's because of photosynthesis and photosynthesizing things. Life needs that. I've got a meter here that I've just turned on. The same meter I measured out there is beeping. I'll turn it off so it doesn't distract us. But would anyone like to guess what the CO2 level in the room is? Okay, 800. I hear 800 over there. Anybody else? Okay. All right, the number is 1800. 1800. So everybody feel okay? Yeah. That's pretty typical. When I used to teach at Princeton, I would often measure in my classroom, and it would be typically 2,000 parts per million, you know, in a lecture. It depends a little bit on how much the institution is willing to spend on heating and ventilation. So the church here is pretty stingy. They're not circulating very much air through this room. But in the air conditioning system, there's a meter like this that actually measures CO2. And when it gets too high, it turns on the fans and it sucks more outside air in. But that's what these meters are for. They're not for the likes of me. They're for heating and ventilation people. So CO2 is a very essential and natural part of life. It is the gas of life. And, you know, we're made of carbon after all. Mostly carbon. And we breathe out a lot of CO2 a day just by living. You know, each of us breathes out about 2 pounds of CO2 a day. That's a lot of CO2. And, you know, multiply that by 8 billion people and 365 days a year. You know, just living people are a non-negligible part of the CO2 budget of the Earth. But nevertheless, we are living through a crusade against so-called pollutant CO2. People talk about carbon pollution, you know, that every one of us is polluting our Earth by breathing, you know. If you want to stop polluting, well, I won't suggest what you do. But, you know, crusades have a way of turning out badly. You know, even the first crusade supposedly to rescue Jerusalem from the hands of the infidels was really not about that at all. It was power, it was money, and it caused enormous damage. I mean, the bitter feelings between our society in the West and the Muslim world go back to some extent to the Crusades. And so crusades really are something we should avoid, but we're in the middle of one now. The Crusaders would say, Deus vult, God wants it, and apparently God wants us to commit suicide. Now here is real pollution. This is Shanghai. If you've ever been in Shanghai, you'll notice that you can just barely see the bottle opener building and Pearl Tower there. But if you can see pollution, then it's not CO2, it's not nitrous oxide or methane. These are completely transparent gases. The room here I've just shown you is full of CO2, but you don't have any trouble seeing me or me seeing you. It doesn't have any effect on visible light. The thing that's magic about these greenhouse gases, they're all greenhouse gases, is that they are very opaque to thermal radiation. So, you know, the heat radiation that I'm emitting would not reach you if you could see thermal radiation. So a rattlesnake could not see me from that distance, or vice versa, because he has pits to sense thermal radiation, but we would be shielded from that by a few meters of air. So greenhouse gases hinder the transport of thermal radiation, which is what the Earth makes, but they have no effect on sunlight or negligible effect on sunlight. Now, we're doing all sorts of crazy things because of this alleged pollutant. This is my wife, Barbara, down near Princeton, where more and more beautiful meadows are being covered with black solar panels. This particular site now is just wall-to-wall panel. There's no meadow left. You know, it doesn't work very well. It doesn't work at all at night. It doesn't work on cloudy days. It's given our latitude, it doesn't work terribly well in the middle of the winter because of the angle of the sun. But nevertheless, we're doing it. So we're being misled into climate hysteria. And if you haven't read this book, I highly recommend it. It was published first in 1841, called Extraordinary Popular Delusions and the Madness of Crowds. And it's as relevant today as it was then. And what it describes, you will recognize if you read it. You're seeing it playing out once again in our generation with climate. It's an extraordinary popular delusion. So it seems to be built into human nature that we do these things. Here is what Mackey had to say in his introduction. In reading the history of nations, we find that like individuals, they have their whims and their peculiarities, their seasons of excitement and recklessness when they care not what they do. We find that whole communities suddenly fix their minds upon one object and go mad in its pursuit, that millions of people become simultaneously impressed with one delusion and run after it till their attention is caught by some new folly more captivating than the first. And that's what we're in now. By the way, this book was required reading if you work for Bernard Baruch. You know, Bernard Baruch had the good sense to sell his entire portfolio in 1929, and he made a boatload of money. And so anyone who worked for him in his organization had to read this book and had to be examined by Mr. Baruch to make sure that he got the message, which was avoid groupthink at all costs. No, yeah, I'm a physicist. You know, I'm proud to say that no one could call me a climate scientist, but I know about climate. I know a lot about climate. And I was a co-author of one of the first books on effects of carbon dioxide. This was 1982, so, 40 years ago, 41 years ago. And this was a study done by the Jason Group, which I was a member of. I was chairman for a while. And it had really good people. There are a number of Academy members on that list of authors. And I was one of them, and I'm ashamed to say we got the wrong answer like everybody else. The key number for global warming is how much do you warm the earth if you double CO2 concentration? That's called the climate sensitivity. So we basically guessed, and I can assure you it was a guess because I was there when it was written, that it was about 3 degrees centigrade. You double CO2, you get about 3 degrees centigrade. It was not based on any hard calculations. It was because of groupthink. That's what everybody else thought. And so that's what we thought. Now, in my defense, one of the reasons I didn't pay much attention to this, I was working on something at this time that I thought was much more important. And so let me tell you about that so you get a feeling for why I think I'm qualified to pontificate about this subject. So during that summer, it was just the beginning of the Strategic Defense Initiative of Star Wars. And you probably remember that President Reagan didn't like the mutual assured destruction dogma that we were living under then, that if we were attacked by the Russians, we would simply annihilate Moscow, St. Petersburg, the whole Soviet Union, And Mr. Reagan really didn't want to push that button. And so he wanted some way to defend the United States so that we didn't have to have this mass suicide pact. And among other things, we considered using high power lasers to burn up incoming missiles. And it's not that difficult, even in 1982, to make a megawatt laser on the ground and a megawatt of power on an incoming missile even a warhead will burn it up, and it will cause no damage. But here's the problem, you know, if you take the 1 megawatt laser on the ground and you send it toward the missile, by the time it gets to the missile, the beam, instead of focusing all the power on the missile, breaks up into hundreds of sub-beams, speckles. And this was something that was well known to astronomers. You have the same problem when you're looking at distant stars and galaxies. You know, if you have a big telescope and you focus the distant galaxy on a photographic plate, instead of getting one image of a galaxy, you get hundreds of them. You know, it's a speckle pattern. And the reason for that is pretty well known. It's because the air above us has patches of warm air and cool air. So when starlight, say, comes toward us, as it comes through the air, it goes a little bit faster in the warm air and a little bit slower in the cool air. And so what would have been a flat wavefront coming in from the star, by the time it reaches us, is bent up like this. So you get this bent wavefront coming into the telescope, and when you try to focus it, it gets deflected into all these speckles. It's bent in all directions. I can't do that very well here. And the astronomers knew how to fix this. It turned out that, you know, they've been worried about this since the days of Isaac Newton. Newton knew about this problem. And if you can measure how much this wave is bent, then you can bounce it off a mirror, which is bent in the opposite direction. And when the wave bounces and it comes up, it's absolutely flat. And that's called adaptive optics. And it actually works. It works beautifully. And then when you focus the corrected beam, you get a single spot instead of hundreds of images. So that was adaptive optics. And the trouble with that is that if you look at the night sky, there are only 4 or 5 stars that are bright enough to have enough photons to do the measurement, you know, of the distortion of the wave. And so we had a classified meeting in 1982 summer. There were a number of Air Force officers there who explained the problem. They were responsible for trying to put together a high power laser defense, and they explained this problem. And I was in the meeting, and just by chance, I knew how to solve it. And I said, look, by chance, I know how to solve this, because you can make an artificial star anywhere in the sky by shining a laser tuned to the sodium frequency onto the layer of sodium that's above our heads at 100 kilometers, 90 kilometers. And so there was some disbelief, you know, why is there a layer of sodium atoms? But I knew there was. And to their credit, after grumbling and doing a lot of due diligence, they led a contract for a big sodium laser. It was several $1 million. They built a secret observatory in New Mexico, south of Kirtland Air Force Base. And I must say, I was getting a little nervous then, because they were spending all this money on this, you know, half-baked idea. It was, well, it's actually, you know, more than half-baked. But fortunately, they turned everything on and it worked the first time. And so it was very secret for over 10 years and only declassified after the collapse of the Soviet Union. So if you go to any big ground-based telescope today, you'll usually see 1 or 2 of these sodium lasers pointing up to the sky at night. And so it makes a big difference in quality of ground-based observations. It's not a problem for the Webb telescope in space, but it is a big problem for the ground. All right, now we're going to talk a little bit about fundamental science of CO2. Of course, the rap on CO2 is it will cause intolerable global warming, you know, all sorts of other horrors. And what I'm going to tell you is that actually it's a very puny tool to do anything to the climate. So you have to remember that there is no single temperature of the Earth. The temperature here is different from outside, or especially if you go up. If you go up, the temperature drops very rapidly. And I gave this talk in Australia a week or 2 ago, so I pointed out to the Australians that at their highest mountain, there's a hotel at 1.5 kilometers, Hotel Kosciuszko, which averages about 10 degrees colder than Melbourne. And so the cooling per kilometer, 10 degrees per 1.5 degrees, which is about 6.6 degrees per kilometer, is called the lapse rate. That's a pretty typical lapse rate. It would be the same lapse rate you would measure here if you went up 1.5 kilometers. You'd find it approximately 10 degrees colder than it is here in New Providence. And that cooling continues up to the troposphere, which is typically 11, 12 kilometers. It's a little bit higher in Australia than it is here, because we're further from the equator in New Providence. And then the cooling stops. And that's because at the troposphere, and that's where jet planes like to fly, or a little bit higher, is where the churning of hot and cold air from the atmosphere stops. Today, you know, if you look, what's the heat transfer out of New Providence? Mostly it's warm parcels of air rising up and cool parcels of air coming down. It's not radiation at all, it's convection. And it's the convection that sets that rapid drop of temperatures, 6.5 degrees per kilometer at low altitudes. It's a little faster at higher when the air dries out. Okay. Now here is the most important view graph of today. And so I'm going to take some time to talk about this view graph. And this has two distinguished physicists on the right. At the very top is Max Planck. And in the year 1900, Max Planck published a formula for the blue smooth curve you see on the view graph. Now, what this view graph shows is it's the thermal radiation coming out to space through clear air, no clouds, versus frequency. So the frequency goes left to right, and for thermal radiation, you typically use the spatial frequency, the number of waves per centimeter, wave numbers they call it. And going up is watts per square meter, or maybe milliwatts per square meter per wave number. So that blue curve was actually known empirically. Lots of experimentalists had measured it in the late 1800s, but nobody could figure out what it was. And it was really completely at variance with classical physics. And thank goodness for that, because classical physics said this blue curve would go up to infinity as you go down to the origin. So it was called the ultraviolet catastrophe. You know, it was a real problem. And so the solution of this problem by Max Planck was really the invention of quantum mechanics. So a lot of people, when they talk about quantum mechanics, they think of, you know, accelerators and all sorts of things, but it really came from the study of heat radiation. That's what drove it. Now, if you look down at the Earth, you don't see this blue curve from a satellite. What you see is very close to this jagged black curve here, and I like to call that the Schwarzschild curve. Schwarzschild was a bit younger than Planck, another great German physicist. He died during World War I on the Russian front. You know, I thought at first the Russians had shot him, but no, he had some autoimmune disease that unfortunately he didn't get the right treatment in the, you know, conditions of the trenches there, and he died. But before he did amazing things. He was the first, for example, to solve Einstein's general theory of relativity, give an analytic solution to that. People still use it today. And he also showed how to account for the effects of greenhouse gases that we're talking about: carbon dioxide, water vapor, which is by far the most important greenhouse gas, methane. Now, you notice that the black curve, the area under the black curve is the amount of radiation that actually gets out to space and cools the Earth. So the more that area, the more the Earth cools. And it's only about 70% of the area under the blue curve. So greenhouse gases are definitely slowing the cooling of the earth. There really is a greenhouse effect. It's quite substantial. Most of it's water, but a non-trivial amount of CO2. But the important point that I don't want you to forget today is if you double CO2, what happens is you go from this jagged black curve to a jagged red curve, which is almost coincident. You can only see the difference between the red curve and the jagged black curve right in the bottom of the CO2 absorption emission band. And if you would actually put in the numbers here, you find that if you double CO2, 100% increase of CO2, you decrease radiation to space by 1%, at 1.1%, but one I'll use for convenience. So let that sink in. Huge effect, huge doubling, effect of doubling CO2, at least in the numbers of CO2 atoms. We're far from doubling it today. It'll take a long time. It only causes a 1% change. So CO2 is a very poor greenhouse gas. It's not an efficient greenhouse gas. And now let's say, if you take all the CO2 away, focus on this view graph again, you go to the green curve. So going from no CO2 at all gives you the green curve and the black curve. They coincide, except in the CO2 band. There's a huge effect of going from 0 CO2 to 400 parts per million, for which this calculation was done. But going to 800 parts per million, it almost doesn't matter. So you get all of the effect in the first little bit of added CO2. Now you could ask, how do you know that you know how to calculate correctly? And well, this is sort of my professional field, so if I know how to do anything, I know how to do this, but this is a comparison of what we calculate compared to what's observed. So on the right, you see some measured spectra of thermal radiation coming up to satellites. They've got interferometers there that do these measurements. They're beautifully calibrated. And on the left, you can see our model calculations. You really can't tell the difference. So there are not many parts of the climate narrative that you can actually do a calculation that is 1 or 2%. But this is one of them. You really can't make a mistake here. So it's really true that doubling CO2 only causes a 1% decrease of radiation. IPCC gets the same answer, so this is not really controversial, although they will never show you the curve or tell you that it's 1%. You know, that would interfere with the narrative. Okay, so this is radiation to space. So how do you change that into a temperature? Nobody cares about radiation to space. You know, they're worried that, you know, we'll get intolerable warming of the surface of the Earth where we live or other parts of the atmosphere. And so here again, you know, it's important to do the first order calculation. Those of you who know a little bit about doing calculations at various orders know that very often the first order calculation is almost correct. And there are many cases when you go to a correction, a higher order calculation, the result is much worse. So the orders are not like normal converging series. They're like asymptotic series where as you add more terms, the answer actually gets worse as you try to make it better. This is well understood, and it certainly happens in physics. It was a big problem with quantum electrodynamics. It was an asymptotic series. So it took some real genius to figure out how to get around that. But the warming comes from this first formula, the T to the fourth, the Stefan-Boltzmann formula. It says that the flux goes as the fourth power of the absolute temperature. And it's got a couple of coefficients. There's the emissivity epsilon. If it's a black body, then epsilon is 1. And then a universal coefficient, sigma, the Stefan-Boltzmann coefficient. Stefan, who's shown here on the upper right, was a Slovenian physicist. He worked in Vienna in the mid-1800s, later 1800s, and he actually found this formula empirically. you know, until he did just splendid experiments, there were all sorts of crazy assumptions about how thermal radiation depended on temperature, and all were very complicated. And he found that actually the dependence goes as this extremely simple t to the fourth, absolute t to the fourth. So that was his first great discovery. But he made another discovery which was equally great, and he discovered this graduate student who's on the lower right, and that's Ludwig Boltzmann, not when he was a graduate student, a bit later. But when Ludwig showed up to Professor Stefan said, well, I've discovered this interesting formula. It says that thermal radiation goes at the fourth power of the temperature, and can you figure out why? I can't figure out why it does that. And Boltzmann studied it for a few months, and he came in and he said, I've solved it. And it turns out it's amazing. Those of you who know a little bit about this will recognize it as one of the just gems of theoretical physics, but it depends on simply the properties of radiation, how much pressure it exerts on its bounding and on thermodynamics. So it's a combination of thermodynamics and the theory of electromagnetic radiation, a very simple proof that you can write down in 4 or 5 lines. But we'll use that here, and this says because of that fourth power here, if you do a little simple calculus and say, I want to keep that flux the same because that cooling flux is provided by the sun. So if the sun continues to heat the Earth at the same rate, but you decrease the radiation to space, that will mean the Earth will start to warm up. You know, we're getting more energy in than we're shedding to space. And so this means that the temperature only has to increase by 1/4 of a degree. 0.25%, I should say. 0.25% increase of temperature will compensate for a 1% decrease in radiation to space. So you can do the first order climate science in your head, and it says that the warming from doubling CO2 is 0.25% of the absolute temperature, which is around 300. So it's less than 1 degree if you actually put in, it's actually if you put in the right numbers here, the warming is 0.7 centigrade, very small. Now 0.7 centigrade, you know, you really can't feel that. You know, air conditioners won't trip on and off if the temperature goes up 0.7. So it's really a problem if you're in the climate science community. So what do you do about this? You know, if it's only this much, then there is no climate emergency, no matter what people do. It's just not enough to matter. And so what IPCC has done is they've assumed enormous positive feedbacks. So the small direct warming from CO2 is supposed to be amplified by factors of 4, 5, 6. And, you know, because CO2 is such a puny greenhouse gas, it's not a very potent greenhouse gas. So in academia, I like to say it's affirmative action for CO2. You know, it's not very good at warming, but if you assume lots of feedback, you can keep the money coming in. All right, so the problem with that, those of you who have a background in physical chemistry and physics know that most natural feedbacks are negative. They're not positive. This is even dignified by the name of a principle. It's Le Chatelier's principle. Le Chatelier was a French chemist who first enunciated this, but when a simple system in thermodynamic equilibrium is subjected to a change in concentration, temperature, volume, or pressure, we've got a change in CO2 concentration. Number one, the system changes to a new equilibrium. And number two, the change partly counteracts the applied change. So this says that the 0.7 degree of warming from doubling is probably an overestimate because there are probably negative feedbacks operating in this very, very complicated climate system that we live in. The atmosphere, the oceans, everything is nonlinear, but so are all of the systems that Le Chatelier considered. For those who have a little trouble with quantitative arguments. I like to use this as an example. If you have a barn and you put a good coat of red paint on it, you get the barn in the upper left. It looks very nice. And you might think, well, I'm really fussy. I want a really red barn. I'm going to put a second coat of red paint on it. And if you do that, it won't make any difference. So the lower left is the barn with 2 coats of red paint. If it's good paint, one paint has been designed by the paint manufacturer to be enough, and another coat won't make any difference. And so our current atmosphere with 400 parts per million of CO2, or perhaps it's 430 or so by now, it's definitely going up. And I personally think it's mostly from combustion of fossil fuels. But it's already saturated. It doesn't matter if we double it, because it will be like these 2 barns. If you double it, the radiation to space will hardly change. And I showed you that quantitatively. Let me just go back and so this is the red barn analogy. The first coat of paint is the jagged black line, and the second coat is the jagged red line. It's a little different, but not enough to matter. Now let me, I talked about CO2 being the gas of life, and I can't avoid saying a few words about its benefits. You know, I hope told you that it's not likely that it's going to be a danger to the climate. But more than that, it's a huge benefit to life on Earth. And what's a stupid thing? Well, this is a field of what? What's this crop? Soybeans. It's a field of soybeans, and it's been genetically modified. How do I know that? Yeah, no weeds. It's no weeds. You know, so the farmer planted the seed, and of course the weeds came up, but then he went over it with herbicide. It killed the weeds and it left the soybeans. So he gets a much bigger crop. This is, by the way, forbidden in Europe. That's why we have such cheap soybeans here, and Europeans pay 2 or 3 times as much. But all plants grow better with more CO2. Soybeans are growing better today than they were 50 years ago, and that you can measure and quantify it. The yields are up by several tenths of a %. And it doesn't matter whether it's soybeans or weed. This is a common weed in New Jersey, velvet leaf. If you have got a garden, you will recognize it. But these are controlled experiments at the glacial levels, at the last glacial maximum, where the weed can just barely survive, and gradually increasing amounts of CO2. This continues as you add more. So plants are really starved for CO2 today. You know, we know plants need many essential nutrients. They need nitrogen, phosphorus, potassium. The most important of all, they need water, but they also need CO2. And like many of the other nutrients, CO2 today is in short supply. CO2 helps plants. Okay, I'm going to just state them. One is that if you got more CO2, plants need less water. That's really important. And if you're a gardener or farmer, you know that every year or two you have a bad drought, and it affects the growth of your crops. So the effects of droughts are much less if you have more CO2. The second benefit is that there's less harmful photorespiration. We talked about the respiration out there in the cemetery, increasing CO2 levels, and that turns out to be to have a problem that goes back to the evolutionary invention of photosynthesis. I'll say more about that in the next slide or two. But here is what is this damn thing? I don't know why. Yeah, I don't know. Well, I'll leave it there. Let me say a little bit about how plants work. On the upper left is an elm tree leaf. And the elm tree is a C3 plant. That most plants that you see around us are C3 plants. They have a very simple, very efficient photosynthetic mechanism. It was the one worked out by Calvin and Berkeley in the late 40s, early 50s. And the plant has to get CO2 to combine it with water, and it gets it from the air through the little holes in the leaf. So CO2 molecules diffuse into these little holes, the stomata, and at the same time, the plant is wet, you know, the leaf is quite moist. Water molecules diffuse out the other way. And the partial pressure of water is 100 times greater than that of the partial pressure of CO2. So you lose typically 100 water molecules for every CO2 molecule you capture and incorporate into sugar and other organic molecules. So the major benefit of CO2 in practice is that it allows plants to grow leaves with fewer holes. If there's more CO2 in the atmosphere, you don't need as many holes in the leaf, you know, to let CO2 diffuse in, and therefore you don't lose as much water. And if you look at an elm leaf in a herbarium, you know, from 1850, and you compare it to an elm leaf today, the elm leaf from 1850 had noticeably more holes, you know, 30 or 40% more holes per square centimeter than the one today. So plants are not dumb. They've been through fluctuations of CO2 many, many times over geological history, and they're designed to grow leaves with just the right number of holes in them to be adapted to the CO2 levels they happen to be living in. There's a second variety of plants. They're not nearly as widespread, but a number of them are important. Corn, American corn is one, and sugarcane is another, which have this C4 photosynthetic pathway. And that's designed to cope with the almost famine levels of CO2 that the world is in today. And so at the current low levels of CO2, C4 plants are able to outperform C3 plants. And the history of that is very interesting. It goes back to the invention of the enzyme that actually takes a carbon and attaches it to a water and a sugar and does the photosynthesis. It's a big, complicated enzyme. Let's see if I can get this. It's called Rubisco for short. It's ribulose 1,5-biphosphate carboxylase oxygenase. When this was invented, which would have been 3.5 billion years ago, there was no oxygen in the air. And so it turns out that this enzyme that works so well with CO2, it takes a CO2, if it has a few ATP, you know, this will work just fine in the dark. It doesn't need sunlight, but it can fix the CO2 at the expense of the chemical energy in the cell. The cell has to get chemical energy somewhere from sunlight or chemotrophs, you know, in the deep sea vents. But if there's not enough CO2, every now and then the Rubisco enzyme will actually catch an oxygen instead of a CO2 and use the chemical energy to make nasty things that actually harm the plant instead of helping it. You know, some of the products are hydrogen peroxide and ammonia, you know, and so plants are full of all sorts of repair mechanisms that cope with this oxygen poisoning. And that's why that's why plants do so much better in greenhouses if you increase CO2. You know, most commercial greenhouses add CO2. They double, triple, quadruple CO2. You know, it's a trade-off between the cost of CO2 and the improvement of your product. Yeah, CO2 isn't free. So greenhouse operators add CO2. They always have lots of water, so the resistance to drought doesn't matter in a greenhouse. But the suppression of photooxidation is a big deal. Okay, so this is what's happening if you look down from satellites at the Earth. And despite what you may have heard about, growing deserts, actually deserts are shrinking. And that's because regions that were too dry 100 years ago for plants to grow can support plant life now because the plants there do not lose as much water. They don't need as many somata in their leaves. So most desert areas are shrinking from the edges as plants move in, are able to grow at lower rainfall rates. And there are lots and lots of studies of this. There's no question that the earth is greening. This, okay, so let me try and bring this to a close because I've spoken too long. So in spite of what to me are just incontrovertible arguments that there is no climate emergency, CO2 is good for the earth, the campaign to banish CO2, net zero, you name it, has been very successful. And so how is that? How can it be? Here I really out of my depth because now I'm talking about human nature, and I'm really good with instruments and with solving differential equations, but I'm not very good at understanding human beings, and if you look over history, it is hard to understand what they've done in the past, and they continue to do it. But here are some of the drivers, and this is not all by any means, but noble lies, political lies, ignorance, stupidity, greed. So here is in politics, this noble lie is interesting. It goes back to Plato, who discusses it in the Republic, but I'll just read you here. In politics, a noble lie is a myth or untruth, often but not invariably of a religious nature, knowingly propagated by an elite to maintain social harmony or to advance an agenda. And here there's a clear agenda. If you could somehow unite mankind to fight some external threat, for example, CO2 pollution, then we won't fight each other. There won't be wars. So I think many sincere people have latched onto the CO2 narrative partly for that reason. I mean, you can actually read about it in the early writings of the Club of Rome. Okay. Then there are political lies. This is one of my favorites, H.L. Mencken. The whole aim of practical politics is to keep the populace alarmed and hence clamorous to be led to safety by menacing it with an endless series of hobgoblins, all of them imaginary. Where's Mencken when we need him today? Then there's ignorance. This is, there are a lot of ignorant, well-meaning people, but this is one of the most striking examples. In 1415, the Czech pastor Jan Hus was burnt at the stake in Constance in Germany because he had rightly pointed out that that the church in that part of Europe at that time was quite corrupt. This is 100 years before Martin Luther. And so his reward was to be burnt. And so there he is tied to the stake. It was a wet day when they were burning him, and so the fire wouldn't start. And so an old woman who was very pious came up with a load of dry brush, and she dumped it at his feet, and then it would catch fire because it was nice and dry. So his remark supposedly was sanctus simplicitas, holy innocence. And so when you look at the likes of, say, Greta Thunberg, for example, Greta's a nice young woman, but she's a lot like this old woman here, in Constance. Now, this is an interesting thing. This is a theory that when I first heard about it, I really dismissed it as it really can't be true, but it's Dietrich Bonhoeffer. Dietrich was one of the very few German clergymen. He was a Lutheran pastor who opposed Hitler, and many other opposed them, but they ran away to England or to America. But he stayed, right in the thick of things, and naturally he was arrested by the Gestapo, and he was eventually hung before the Americans could rescue him. But he was in jail for 3 or 4 years and under the Nazis, and he had time to think about, how is it possible that Germany, the country of philosophers and poets and musicians and scientists, has been taken over by these thugs, these knuckle-dragging Nazis. And so he at first thought, well, they're just evil. But then he came up with this theory. So I'll read you what he says. It says, stupidity is the real problem. Against stupidity, we have no defense. Neither protest nor force can touch it. Reason is of no use. Facts that contradict personal prejudices can simply be disbelieved. Indeed, the fool can counter by criticizing them. If they are undeniable, they can just be pushed aside as trivial exceptions. So the fool, as distinct from the scoundrel, is completely self-satisfied. In fact, they can easily become dangerous, as it does not take much to make them aggressive. For that reason, greater caution is called for than with a malicious one. And I don't know if you've ever spoken up on this. Yeah, you would recognize what he's saying, but I regularly get phone calls threatening me with death and my wife and children with death, And so what kind of movement is this? Here is an example of that theory it's a letter from Galileo to Kepler. Galileo was lucky. He was only kept in house arrest all his life, but his predecessor Bruno was burnt at the stake for proposing that the Earth moved around the sun. And of course, Kepler was the guy who discovered that the motion was actually elliptical orbits, not circular. He says, "My dear Kepler, I wish we might laugh at the stupidity of the human herd. What do you have to say about the principal philosophers of this academy who are filled with the stubbornness of an asp and who do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times? Truly, just as the asp stops its ears, so do these philosophers shut their eyes to the light of truth." Well, not many people are willing to look at red barns, for example. Then there's the, good old-fashioned greed. This is a quote from Alexander Pushkin, who, the quote says, "If there should happen to be a trough, there will be pigs." And, if you live in academia, I can't tell you how much money has been poured into academia to support the climate narrative. My own university, Princeton, we're building a number of brand new buildings because of all the climate money that's pouring in from Washington and from philanthropies. So greed is with us. And let me finish. This is my last slide, and I'll be glad to chat, take questions afterward. This is what's going to happen to countries that really go to net zero. It will be a disaster. I don't have time to go into all the reasons, but again, the reason I'm doing this, and I hope some of you will do the same thing, is summarized by, again, Dietrich Bonhoeffer, the poor guy who was hanged by the Nazis. If I see a madman driving a car into a group of innocent bystanders, then I can't simply wait for the catastrophe and then comfort the wounded and bury the dead. I must try to wrestle the steering wheel out of the hands of the driver. So I hope you will all help. So that's all I have to say.
Thank you very much, Dr. Happer. It's time for Q&A.
Well, Professor, thanks. I get continuing education credits for my profession, and I'm going to apply for one here. But my brain is full of all of this. So the question is, CO2 is one piece of the climate catastrophe, right? So you have a solution. I deal in projects with mitigating risk and I try to find the root cause. Now, the root cause of what we've done to this planet is too many people. With the population of the planet is 8 billion. I was watching TV and the guy said the sustainability of the planet is 3 billion. So I know you do the CO2, but what about population? Can you guys figure out what we benefit by reducing the population?
Well, that of course, is a very good question. And I think it's true that many people who are in the discussion of CO2 and demonizing CO2 are really worried about population. They don't believe that there's a climate emergency, but they think there's a population emergency. In fact, you know, the German group thinks that the world can only handle 1 billion people. You know, so if you look around here, there are 8 billion people in the world. 7 out of 8 of us here have to voluntarily leave the world. You know, I sort of never liked that very much. And I think that, you know, look, if you want to control population, we know the answer to that is you make people prosperous. The way you make people prosperous is you give them, you know, affordable energy. Every country in the world that's prosperous, United States, all the European countries, Italy, Japan, even China now, population is not in, you know, women are not having children fast enough to sustain the populations. The population is dropping. US population would drop if we only relied on our own American women, you know, to replace the population. The only thing that's letting us grow is immigration. So in my view, you know, the best thing we could do is to bring the benefits of fossil fuels to people as long as they last, and they'll last a long time. And in the meantime, figure out what we do after that. Yeah.
Thank you. The next
Online,
is
Alex.
online from Al Aho. Please ask your question now.
Well, thank you for a most interesting talk. I have heard that the global mean surface temperature has been increasing in the last few years. Is that a good measure of global warming? And if so, what is causing this increase in DMST?
It's observed that the sea surface temperature has been increasing, not very much, mind you, but you can measure the increase. And it's increasing particularly rapidly this last year because we've got an El Nino developing, a big one. And, you know, most of the sea surface is actually in the Pacific. And under normal conditions, you've got strong trade winds blowing from the Americas toward Australia and Indonesia. And so they pile up warm surface area to an enormously deep, warm pool off of Indonesia. And last year, the winds stopped almost. And so all of that warm water that was hidden below the surface is now spread out over the surface. And so that's making the entire world look quite a bit warmer than it was a year and a half ago. Now, what causes that is, I think, you're good to I'm so glad you asked that. I think that's what we should be working on. What causes these regular, or rather irregular El Ninos, La Ninas, and the other things that really affect the climate? The climate has never been stable in history. You can show that from all sorts of geological proxies. And for example, the climate warmed enough in the year 1000, 1100 that they were farming the south of Greenland. You know, you can look at the old Norse homesteads there, and they grew barley and things that won't grow there today. That clearly had nothing to do with CO2. So I think the key question is, how do we really understand the climate? We've been deflected by this maniacal focus on greenhouse gases, which almost certainly have very little to do with the major changes of climate, which can be a big problem for humanity. So I don't know if that's a,
Next, Tom Pate.
Your presentation is very interesting and a very contrarian view. I wonder how your compatriots react to your opinions. In particular, Dr. Oppenheimer, who is, I believe, the environmental and climate scientist at Princeton.
well, Dr. Oppenheimer and I very seldom interact. Let me just say that one difference is his salary depends entirely on climate alarm. I don't get a nickel for this, but he's very well paid, for keeping this going.
Next question.
Thank you very much for an interesting presentation. But how do you account for the fact that recent empirical data have shown an excellent correlation between CO2 concentration in the atmosphere and Earth surface temperatures, and also the fact that we know that other planets in our solar system, which have extremely high CO2 concentrations, also have extremely high temperatures?
Okay, well, how do you account for the fact that models fit the temperature? Well, it's simply curve fitting. It has no really scientific basis, and you have to ask yourself, well, if CO2 is the thing that drives temperature, why did we not see big changes of CO2 during the Norse settlement of Greenland? There was almost no change. CO2 did not go up at that time, or it went up maybe 1 or 2 parts per million, not very much. Or the little ice age that followed that, when it got much colder, the Thames River froze regularly, the Dutch were skating on their canals. That's been a long time since that was possible. And again, CO2 hardly changed. It did not go down. So it's completely clear that something causes the climate to change that has nothing to do with CO2. And the change that we're seeing now, you can't distinguish from these previous changes when CO2 didn't change at all. There's a famous interchange between my friend Freeman Dyson from Princeton and Enrico Fermi, where Freeman was boasting about a new theory he had for fitting new results in nuclear physics. And Fermi said, well, Dr. Dyson, how many parameters does your theory have? And Dyson says, well, let me see, I think 10. and Fermi says, 10? Well, that's ridiculous. With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And so it's curve fitting,
Next question, please.
Okay, sorry. So the first one, quite simply, is if we do achieve zero emissions at some point, how long will it take for the carbon dioxide concentration to decrease by substantial amounts, say a factor of 2?
Okay. So if by magic we were to stop all human emissions, I think is the point, is that right? What would happen to CO2 concentrations in the future? Well, people are arguing about that today. My own guess is that the decay time is probably of the order of a century, that it would decay exponentially by about that time. But it's a very controversial topic. There are people who say, well, it has to be even 1,000 years because, the thermohaline circulation of the oceans is on the order of 1,000 years for, deep water from off of Norway to come up in the Pacific. And so that should be the long time constant, but there's no reason to assume that that's the time constant. Most of the human CO2 is still in fairly shallow water. So at least for the immediate future, I think probably a century is the right guess. It's not 1 year and it's not 1,000. Okay, yeah.
May I ask another question? It's very short.
Yes. Yeah. Okay, so the big difference between like the ice ages in the past and so forth is that the warming is happening very rapidly now, much more rapidly than in the past. So I would have to assume that there's something causing it, and if it's not CO2, then I wonder what could it be?
Okay. So the question was that CO2, the temperature is warming much more rapidly than in the past, I think was your point. I don't think that's true, because if you look at the warming at the time of the North settlement, it was just the same as today. It was, you know, from the proxy records, and they're pretty good records of that. And, you know, the warming at the end of the last glacial maximum was much, much faster than today. You know, it was, you know, that was when there was a mile of ice over Manhattan, but it melted tremendously quickly. So we're not in a period of unusually fast warming, but you did ask the right question, is what is really causing the change? I commented on that before. I think we've set the field back at least 50 years by not focusing on these real things that are clearly not due to greenhouse gases. One of the theories, you know, the main driver of our weather is the sun. And so my own guess is that when the truth is finally revealed about climate, that it will turn out that clouds have been the main driver. And people don't like to work on clouds because they're, you know, they're very messy and hard to model. And you can't get this 1% agreement I pointed out for clear skies. You know, and so that's why I don't work on them either. They're very hard to work on.
Question online from John Mikeda.
Thank you, Dr. Happer. Very thought-provoking presentation. I have two questions. One has to do with the curves that you have shown, where you've shown from the radiation pattern from the Earth, there was no difference between 400 parts per million of CO2 versus 800 parts per million of CO2. Now, this appears to be a measurement, and my question is, how did you get curves with 800 parts per million, since the Earth never really had that kind of concentration of CO2, at least not recently?
Yeah, thank you. If I understand it, is how do I get the curves for 800 part per million? That's a calculated curve. You know, of course, you can't add 800 parts per million to the Earth and measure it. But to try and give you some confidence that I know how to calculate it, and actually the IPCC gets exactly the same number we do, to within a few percent. I showed you pictures of satellite measurements of spectrum coming up. And so the measurements in today's concentrations agree with what the model calculates. So that gives you some confidence that if you increase CO2 concentrations, you will still get the right answer. If I'm wrong, so is IPCC.
Okay, I have another question, if I may. It has to do with the water amplification. You mentioned that the water amplification is factor 5. Can you substantiate where you got these numbers from?
Well, he talks about water amplification, I think I heard. And this is one of the favorite feedback mechanisms. I mentioned that if you, to first order calculate how much warming you get from doubling CO2, you get less than 1 degree. And so you need something bigger, and water amplification is a favorite. In fact, my Princeton colleague Manabe was even given a Nobel Prize for proposing this. I showed you the picture of the Earth's atmosphere. It cools as you go up very rapidly, 6.5 degrees per kilometer, a little faster as you go higher. And if you can get water higher up into the troposphere than it is today, it will be colder and it will radiate less, and that will be a positive feedback mechanism. It will suppress radiation to space more than just the CO2 doubling alone. So that is, the problem with that is you can measure the water vapor in the upper atmosphere. It's actually going the other way, it's going down. Right, so if it were true that water vapor concentrations were increasing in the upper troposphere, that would be a major climate driver, but they're not, they're decreasing.
Okay, I have a question too. Dr. Happer, you have paraphrased a great deal of theory as a physicist. And you've relied on the body of science that's been developed over centuries. Science works with institutions that are like gatekeepers and with certain customs. And one of those bedrock customs is peer review. And we have a very big scientific establishment that's devoted to that. You expressed a certain contempt for the established climate science, and you say that it's self-interested. But nevertheless, your own science, which is contrarian, does not seem to be backed up by very much in the way of peer review. And I'm talking about legitimate scientific sources. Also, you've said that there's a lot of self-interest, and you've talked about stupidity. But you're very much in the minority. So I looked you up and I found out that you have founded and also been associated with organizations that are not scientific, but partisan. And they're supported by interest groups such as the oil companies. So my question is, what puts you ahead of everybody else?
Well, I think the question is, since everybody disagrees with you, they must be right. And so this is kind of the consensus argument that, science is determined by vote. If you don't like the law of gravity, we'll repeal it. It's inconvenient, it's hard for transportation. And so it's true that, if you look at most people who identify as climate scientists, they all completely agree with the narrative, the standard narrative that we're in a climate emergency. Just send more money to my research grant next year and we'll help you. But that doesn't make it true. There have been lots of cases like this, when science gets politicized. One of the more egregious ones was the Lysenko area in the Soviet Union. Lysenko was a agricultural extension agent in Ukraine or somewhere, and he came up with this idea that the whole of genetics was wrong, and that you could teach plants to grow below, above the Arctic Circle, you know, if you just followed Marxist-Leninist, you know, ideas. It was absolutely crazy. And many brave Russians in the Soviet Union opposed this. But the Communist Party took it up. The government backed Lysenko. So you were lucky if you know, if it was discovered that you were teaching about Mendelian genetics, you know, and wrinkled peas and smooth peas. You were lucky just to get fired. You know, many were sent to concentration camps, and 1 or 2 were sentenced to death. That continued for 40 years. It went on for a long, long time. And well, in our own country, let's talk about genetics, eugenics. You know, and starting around 1900, you know, eugenics was all the rage. Everybody believed in eugenics, you know, that the good old Anglo-Saxon race was being destroyed by all of these immigrants, you know, Italians, low IQ Italians, and Eastern European Jews. And, you know, every little town had a eugenics meeting. Providence probably had a eugenics club where the ladies would meet every Thursday and wring their hands about the corruption of the gene pool. It was all lies. It was from beginning to end. And yet, you know, it was official science and it was peer reviewed. They had journals. And the only thing that finally stopped it was that the Germans, with due gratitude to the Americans, took it over, you know, and yeah, with typical German thoroughness, carried it through to the logical extreme. So, you know, science has a very bad reputation. You know, if you look at the history of science, again and again, the majority has been on the wrong side.
Next question online from Miguel Velez.
Thank you, and thank you for your previous question. I appreciate it. My original question, I have to modify it and actually ask 2 questions because of a comment you made. But my original question was about your opinion on the melting of the glacier ice caps, or the glaciers that are in Greenland or whatever. What is the cause and what would be the effect of those if it's not global warming? But my second part of the question is, you mentioned to give people fossil fuels. Is there, in your opinion, is there something inherently wrong with hydrogen fuels or solar fuels or hydro fuels that are not fossil fuels? Because one of the other problems we have that you haven't mentioned is methane, which is a very strong component of pollution. So 2-part question: what about the ice caps? What's causing it, and what do you think the effect is? And the second is, what is your opinion on natural renewable fuels?
Okay, well, let me try and be sure I remember. The first part of the question was about the melting of the Greenland ice. I presume Antarctica would be included there, and perhaps some glaciers. And the second was about non-fossil fuels, hydrogen, for example. So with respect to the first, you have to remember that it's not entirely temperature that determines whether ice persists. It's also the source of snow. And so it's pretty hard to melt the ice in Greenland because it gets a lot of precipitation as snow from the Atlantic, you know, up high altitude, 10,000 feet. So it falls down as snow. And that's true of glaciers too. For example, Kilimanjaro Glacier advances and recedes. It's almost on the equator. But what determines whether it's growing or shrinking is the amount of snowfall on top of Mount Kilimanjaro. And so the temperature hardly changes on top of Mount Kilimanjaro, but the snowfall changes a lot. So I don't know. I won't say any more about glaciers, but if you want to study them, you have to include both terms, the source of the glacier, of the ice, and what causes it to melt. I don't think there's any problem with Greenland for a long, long time. Now, with respect to non-fossil fuels, I think it's clear that, I don't know when, but we'll run out of fossil fuels at some point. And I don't think that will be in the lifetime of even my grandchildren, but it will have to happen. And it would be nice to be prepared at that point to replace them. There's nothing like a gallon of diesel fuel, you know, to be a convenient source of energy, or to fly an airplane or to drive a truck. And could you make a gallon of synthetic fuel? And hydrogen, fine, you can make hydrogen by electrolysis if you have lots of cheap energy from the sun, say, or from wind power. But hydrogen is singularly difficult to handle. It's hard to transport, it leaks, it's you know, it's dangerous. So rather than hydrogen, I would guess that if you make hydrogen, you would combine it with something that is a better carrier. And so my guess is that in 500 years, if the human race survives its innate stupidity, that it will be making synthetic fuels that will be based on carbon. You know, you'll have plenty of energy from some source, maybe fusion, maybe fission, and you will combine the carbon from things like limestone, or perhaps from the atmospheric CO2, with hydrogen to make hydrocarbons. It's hard to beat a hydrocarbon as a transport thing, and it doesn't have to be made underground. You can synthesize them if you are clever enough and have enough cheap energy.
Thank you. Next question, Alan.
Oh, your talk has triggered a memory in mine of a back of the envelope calculation I did about 50 years ago. And I was intrigued by what was causing the global warming phenomenon. And I wasn't getting in down into the weeds with all these subtle theories of gases and CO2 and so on and so forth. I just did the simple back of the envelope calculation as a physicist, making great oversimplifications, like take a spherical cow, but basically it was, if you assume the starting point is that the Earth is in thermal equilibrium with the sun, the energy coming from the sun is balanced by the amount being radiated back by the Earth, and hence using, like you did in one of your slides, the Stefan's law, and just a bit of mental arithmetic at that point, on the assumption that assuming emissivity stays the same and so on and so forth, what perturbs that equilibrium? Let us assume it is all the energy that is being generated on the Earth, and that is trapped on the Earth by the clouds, to the extent it is, and the emissivity is not changing that much. The calculation yielded something like 0.5 degree centigrade, very comparable to what you is such a simple way of looking at it, thinking of energy as the prime mover, and then all of these other little mechanisms are going on.
Well, thank you very much. I think what you described is essentially all you have to do, and that's certainly all I did. You balance the incoming energy from the sun with the radiation back into cold space from the Earth,
Yeah.
We've come to the end of our Q&A. Mike, please come up and thank our speaker.
Thank you. Thank you very much, Professor Happer. I very much appreciate it. Just amplifying one comment you made about eugenics. Watson and Crick discovered the double-stranded DNA. Watson was a strong proponent of genetics to his dismay. I just want to mention that point. In any event, I thank you for your provocative presentation. Hopefully it makes everybody think about this important issue. And as part of the old guard, thank you. We were founded in Summit, New Jersey. At that time, one of the leading producers of orchids. And I present you with essentially a certificate of appreciation for your presentation. And thank you.
Thank you very much.